Okay, and so the last thing we want to look at as part of this statistical inference topic, and the last thing we therefore want to look at in terms of content in Maths Methods Unit 3-4, is this idea of confidence intervals. So we want to look at, well, how confident can we be in what we're learning from the sample? How confident can we be that that is representative of the population? And we want to look at this idea of a confidence interval. So suppose that it's known that 14% of Australians are living below the poverty line. That's a stat from this source here. It's a bit old now, 2014. So we know, therefore, that the population parameter P is 0.14. In practice, we wouldn't know this parameter, and we would instead be trying to estimate this. And we might do this by taking a random sample of 100 Australians. So if we select one sample of 100 people and find that 10 are living below the poverty line, then the value of the sample proportion is p hat, which is 10 out of 100, and so that is 0.1. If a second sample of 100 people is selected, and this time 15 people are living below the poverty line, then the value of the sample proportion for this sample is 15 out of 100, or 0.15. And we can continue in this way. After selecting 10 samples, and I randomly generated these numbers, so after doing this 10 times, the values of p hat that are observed might look like those on this dot plot. So as I said, I did this for a random set of data. So we see that, remember, we wouldn't normally know, but we know that that's actually the population proportion, and obviously we're getting sample proportions that are spread around that, but they're not wildly far away from that. That's 0.19 and that's 0.07, okay? So yes, they're spread around that, but it's not like they're 30% or anything. It's not double. So it's clear that the proportion of people living below the poverty line in the sample is varying from sample to sample. And if we continue to take more samples, we'll begin to see a clearer picture of the sampling distribution. So after 100 samples, each of size 100, the distribution of p hat is this. Okay, so there's 100 different samples. In one of them, the I've changed the data again there. Anyway, in one of them, the sample proportion was 0.06. In two of them, the sample proportion was 0.23. In three of them, the sample proportion was 0.13, etc. So we're starting to get this sense. If we were to take 500 samples, each of size 100, the distribution of p hat becomes this. So we see the more samples we take, okay, and hence the more times we do this, the more normal this is looking. Okay, the more bell-shaped this is looking. And so what we actually know is that, as I said, we previously established that the sample distribution of p hat is a linear transformation of a binomial variable x, such that p hat is x divided by n, where n is the sample size. And we know that for large values of n, the binomial distribution can be approximated by the normal distribution. Okay, so we're seeing here that actually this could be reasonably well approximated by a normal distribution. And we're only looking here at samples of size 100. If we had even larger samples, it would be even better. Okay. So when we do that, when we approximate the binomial distribution using the normal distribution, the mean of the normal distribution is equal to the mean of the binomial distribution, which we already know is p, and the standard deviation of the normal distribution is equal to the standard deviation of the binomial distribution, which we already know is the square root of p times 1 minus p over n. So for a sampling distribution, p hat is x over n, where x is a binomial variable. We already know that the expected value of x is np, which means the expected value of p hat is p. We've already looked at this, and the standard deviation of p hat is the standard deviation of 1 over n, which is this. So those are formulas we already know. And so therefore, if we've got large samples and large numbers of samples, and we can approximate the binomial with a normal distribution, then we can model the sampling distribution with a normal curve that has a mean equal to p and a standard deviation equal to square root of p times 1 minus p on n. So if we return to our sampling distribution, where p was 0.14 and n was 100, then we can model this distribution with a normal distribution where the mean is 0.14 and the standard deviation is calculated by this, which equals 0.035. And when we do that, we see that this is the pink normal curve that we would be using to approximate that sampling distribution. Okay, and we can see that that's a reasonable approximation. So when the sample size n is large, the sample proportion p hat has an approximately normal distribution where the mean is p and the standard deviation is p times 1 minus p over n. Okay, so unless you were told to approximate with the normal distribution explicitly, you wouldn't. Okay, but the point is what we're leading to is this idea of being able to use the normal distribution leads us to this idea of confidence intervals. So we've already seen that when n is large, the sample proportion has an approximately normal distribution, okay, with a mean of p and a standard deviation of this ugly expression. So we've done lots of work with normal distribution already. So we know if the mean is p, that's the center of the normal distribution. And then we know things about, well, 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean. So we know that within 2 standard deviations of the mean, we have roughly 95% of the distribution. So we're starting to talk about this idea of a 95% confidence interval. So here we're interested in finding a range of values within which we can be 95% confident that the population proportion, which we know is the mean, will lie. Okay? And so in order to do this, we need to standardize the above normal distribution. And we'll recall that this is done via this transformation. We take our x value, we subtract the mean, and we divide by the standard deviation. So in this case, our distribution is not about x, our distribution is about p hat. So it's going to be p hat, take away the mean, which is p, and divided by the standard deviation, which is this ugly expression. And when we do that, we've now got our standard normal distribution. So we know from the properties of the normal distribution that if z is between -2 and 2, that's the probability of that's approximately 0.95. But actually we can be more precise than that, because it's actually not exactly at 2 and -2, it's an approximation, okay? And so actually, if we want to know what is that exact value where it's 95%, well, it's not exact, but what's a more accurate value where it's 95%, we can think about, well, okay, if I want to work out what that value there is, let's call that A, then I know if I want 95% in there, plus there's going to be another 2.5% over here, I know all of that has to be 97.5%. So I can use inverse normal. Okay, so menu, 5 for probability, 5 for distributions, 3 for inverse normal. The area is 0.975. It's a standard normal, so mean is 0, standard deviation is 1. And I can work out that that's actually, this A value here is actually 1.959963986, etc. Okay, so we can approximate it better. Rather than using 2, we can use 1.96 as an even better approximation. Okay, we can use an even better approximation if we want, but let's go with 1.96 for now. So we know that probability that z is between -0.196 and +0.196 is about 0.95. It's a better accurate, it's closer to 0.95 than that. Okay, so, however, we recall that z is equal to this. So we want to replace the z with that expression. Okay, so let's go to here, we're going to do that. So z is that. Alright, and so we therefore know if the probability of z being between -1.96 and +1.96 is, sorry, that's a random less than or equal to, it doesn't really matter, remember it's a continuous variable, but let's stick with less than, is approximately 0.95. So therefore, this thing is z. So we therefore know that this thing, the probability of this thing being between -1.96 and +1.96 is approximately 0.95. And now let's just play around with this inequality in here, just to make that a bit neater. So we haven't got this really ugly fraction sitting in here, okay? So what we're going to do is we're going to multiply every side of the inequality by this. Now standard deviation will always be positive, it's a positive square root, so there won't be any issues with our inequality signs by multiplying by that. So we're going to multiply everything by that. So we multiply -1.96 by that, we multiply +1.96 by that, and we multiply this bit in the middle by that, which means we get rid of the denominator. So we now just have p hat minus p. Okay, then I'm going to subtract p hat from all sides of the equation. Now p hat's a positive thing as well, so I'm subtracting something, that's fine, we're not dividing by negative, so we don't switch these around at all. So we're going to subtract p hat, so we're subtracting p hat from there, subtracting p hat from there. I've written it at the front just because that's the more conventional expression, but it's still the same thing, and now we've just got negative p left here. Okay, and now the last thing I'm going to do is I'm going to multiply everything by -1 to get rid of that, which means my signs will all flip around, and so I've actually rewritten it. So if I take that and multiply it by -1, it becomes that, it's on that side of the inequality because we've had to flip the sign around. And if I take that and multiply it by -1, it becomes that, and it's on that side of the inequality because we've had to flip the signs around because we multiplied by a negative. Okay. Alright, so now we've got to a point where we've made this ugly expression, rather than it being about z, it's now about p, the population proportion. Okay, so now we know that the probability that the population proportion lies between this thing and this number is 0.95. So we've now got this interval within which we can be 95% certain that the population proportion lies. Okay. So one of the issues here, though, is that remember that we don't know what the population proportion is, theoretically. We only have the sample proportion. So we're going to have to approximate the standard deviation value using the sample proportion. Okay, so that's one slight error that needs to come into it. So we're going to use this as an approximation for the standard deviation. And so that gives us this. And this is our 95% confidence interval. The probability that the population proportion lies between this number and this number is approximately 0.95. We can be approximately 95% confident that the population proportion lies between this and this. Okay. So we can write the confidence interval in different ways. We can write it as an inequality like this. We can write it just as an interval. As I said, it is a confidence interval, so it doesn't include that number, doesn't include that number. It goes from there to there. Okay, so in the same way that 1 to 5 means 1 is less than x is less than 5. That's all we're doing. We're using our interval notation. And the other way the confidence interval might be written is p hat plus or minus this expression, because that's essentially what those two numbers are. Okay, so this is our 95% confidence interval, remembering that that's a rounded number. Okay, so we could be more precise by using that number more precisely, and that came from this inverse normal you can see over here on the left. And that's about us working out, well, if I want to know what this value is so that either side of the mean we've got 95%, okay, that means that this all the way down to here is 97.5%, and I use my inverse normal to find that that is 1.959963986. Okay, so we can be more precise with the confidence interval by using a more precise value there. In fact, usually I would generate that number and use that exact number in the calculation. So in these formulas, p is the population proportion. We don't know that. That's what we're trying to generate an interval for. P hat is the sample proportion that we've calculated from one particular sample. It's sometimes also called the point estimate or the sample estimate. And n is the size of the sample from which p hat was calculated. And n must be sufficiently large because we are using that normal approximation to the binomial. So if we were only taking samples of 5, this wouldn't really be a good model. So if we've got big enough samples, and look, that sufficiently large measure is a fairly arbitrary thing at this level. Be confident that if you're being asked to find a confidence interval, it's being deemed that n is sufficiently large. Okay, example 1. Given that 120 out of a randomly selected sample of 200 Australians have blue eyes, find a 95% confidence interval for the proportion of Australians who have blue eyes. Okay, I'm going to perhaps think in... Oh, no, let's do it properly. Okay, so we're going to have, we know that the confidence interval, so the 95% confidence interval is p hat minus 1.96 times the square root of p hat times 1 minus p hat over n, comma, p hat plus 1.96 times the square root of p hat times 1 minus p hat over n. Okay, so we need to work out those things. So, given 120 out of a randomly selected sample of 200. Okay, so we've got n is 200, okay, and p hat is 120 out of 200. Okay, so 120 out of 200 is 60 out of 100, so that's 0.6 or 3/5. Okay. Alright, so we know that our confidence interval is going to be 0.6 take away 1.96 times the square root of 0.6 times 0.4 over 200, or 0.6 plus 1.96 times the square root of 0.6 times 0.4 over 200. Okay, so 0.6 minus 1.96 times the square root of 0.6 times 0.4 over 200. Okay, so that is, we should have been given accuracy here. Let's go with, I don't know, 4 decimal places. So 0.5321, comma, and then we need that same calculation but with a plus there, 0.6679. So we can be 95% confident that the population proportion of those with blue eyes is somewhere between 53% and 67%. Okay, can be 95% certain that somewhere between 53% and 67% of the Australian population have blue eyes, is essentially what we are learning from that. Now, we've only talked about, let's go back to this first and then I'll go on to changing the level of confidence. So, in interpreting our confidence intervals, we found that in this previous example, the 95% confidence interval for the proportion of Australians who have blue eyes is this. And this should not be interpreted as there being a probability of 95% that the population proportion will be between 53.2% and 66.8%. Okay, since P is constant, and therefore it either does or doesn't lie within that interval. There is either a 0 probability or a probability of 1. Okay, so it's not about probability, it's about level of confidence of that the proportion will lie somewhere between here and here. So it's important we make that distinction. So the particular confidence interval found is just one of any number of confidence intervals that could be found, each one depending on the particular value of the sample proportion. So we could have had a very different sample. We could have taken a different sample of 200 people and found that only 80 of them had blue eyes, and then we would have got a very different confidence interval. So it's important to understand that the confidence interval you've calculated is just based on one particular sample. Okay, so what we've actually established is that if we were to take lots and lots of samples, in 95% of those samples, the population proportion would lie within the confidence interval that we calculate. Okay, so say for example here in this diagram, we've got 20 different samples. Okay, so we could take in our first sample, that might be the confidence interval we discovered, that might be the sample estimate or the sample proportion, that might be the confidence interval we calculate, and yes, p hat is within that interval. Okay, and what we would find is that if we did 20 intervals, we would expect that one of them, which is 5% of 20, that in one of them, this one, the population proportion doesn't actually lie in the confidence interval. So therefore, we can't be certain that the population proportion does lie in that interval at all. The idea is that if we were to take lots and lots of confidence intervals, lots and lots of samples, in 95% of those samples, the population proportion would lie within the confidence interval. That's actually what's happening with a 95% confidence interval. I think that's pretty much what that paragraph says. So a correct interpretation of the confidence interval would be to say that we can be 95% confident that between 53% and 67% of the Australian population have blue eyes. Okay, it's not about a probability, it's about a level of confidence. And even then, it's quite possible that it's not between there and there, but it's only a 5% possibility of that, potentially. However, to avoid making erroneous claims about the confidence interval, it's easier just to always say a 95% confidence interval for P years, rather than try to interpret it too much. Okay, try not to go overboard with the interpretation of it. Okay, then we want to look at changing the level of confidence. So we used this fact to establish that a 95% confidence interval, this 0.196, came from this probability of the normal distribution, that the probability of the Z score being between negative 1.96 and positive 1.96 is 0.95. And you'll recall that in my calculation, I used the more exact, actually no I didn't in the end. Let's have a quick look at what would have happened. So I did mean to, rather than typing 1.96, to go up here and get my actual value, which is that. And let's see, is it very different? No, it's different at this 1, 2, 3, 4, it's different at the 6th decimal place. Okay, so for all intents and purposes, 0.196 is sufficient, but if we want to be more precise, there's no reason why we can't just quickly generate that number with the inverse normal. It would have been, this one's actually different at the 5th decimal place, 6679 we should have written down, or I think we wrote 6678. Oh no, 6679, yep, so it's fine. Okay, so the whole thing though is this number here is what's defining that we're looking at 95% confidence. So if we were interested in possibly a lower level of confidence, if we were interested in a 90% confidence interval, for example, then we would need to find this number so that this is true. So what we're looking at is in the standard normal, we want to know if 0 is the mean in the standard normal, we want to know between what two values do 90% of the population lie, which means that to use inverse normal, we're going to need to think about, well, all of that has to be 0.95. So if you use menu 553 for inverse normal, and the area is 0.95, standard normal, we find that that is, this number here is 1.64, okay? And so we get this, we find that it's approximately 1.64, and so this number in the confidence interval would be replaced by that 1.64, okay? And similarly, if we wanted a 99% confidence interval, then we're looking at, okay, in a standard normal distribution, between what two values are we going to get 99% of the distribution? So that means there's 1% that's not in there, which means there'd be a 0.5% down here at the bottom. So we want that to be 0.995. And so if we did inverse normal with 0.995, we find that this number here has to be 2.58. Okay, and so we can adjust the level of confidence accordingly. So in general, a C% confidence interval for P is given by this, okay? That number there is going to be the values that we get from using inverse normal, where the probability of Z being between negative A and A has to be equal to our level of confidence, okay? Now, all of that is a little bit irrelevant, to be honest. It is important that we understand the bits and pieces of that confidence interval and where that comes from, but we can actually use our CAS to find a confidence interval. So if we go back to our, blue-eyed example, which is what we're going to be asked to do here in example 2, if we go to menu 665, okay, now we know we need N and P hat, but the CAS actually asks us for different information. It asks us for the number of successes and N. So the size of the sample and the number of times within that sample you're seeing. So actually it's even easier. This 120 and this 200 is what we need for our CAS's confidence interval. So we had 120 blue-eyed people out of our sample of 200, and we want a 95% confidence level. Okay. And there's our confidence level. So we've got our C lower and C upper are our upper and lower limits of the confidence interval. It's calculated P hat for us, which is 120 out of 200 or 0.6. It's calculated the margin of error, which we'll talk about in a minute. And it's also given us N, which was 200. So we get our 95% confidence interval. So let's read fully this example, sorry. Given that 120 out of a randomly selected sample of 200 Australians have blue eyes, find 90%, 95% and 99% confidence intervals for the population, for the proportion of Australians who have blue eyes. Okay, so the 95% confidence interval is the one I've just worked out. It's the same one we just did by hand. And again, let's give them all to 4 decimal places. So that is going to be 0.5321 and 0.6679, okay? Our 90% confidence interval, we just need to adjust sorry, it's not that one. We just need to adjust here. It's going to be 95. That's a bit ugly to see that adjustment. So let's go back to the calculation. So we go to menu, 6 for statistics, 6 for confidence intervals, and we want 5, 1 prop Z interval. I chose 1, sorry. Menu 665. Okay, so we've still got number of successes is 120, N is 200. This time we want a 90% confidence. And so we get that our lower is 0.5430 and our upper is 0.6569. 6569? No, 65, sorry, that's going to need to round up, isn't it? 6570. Okay, and then if we want a 99% confidence interval, so I'm going to just edit here. I'm just going to change where it says 0.9 there to say 0.99. We're going to get that, which is 0.5108 and 0.6892. Okay, so one of the things to notice here is that this one is the widest interval, okay, and this one is the smallest interval. This one's the middle one, okay. So the idea is if we need to be more confident that our interval contains the population proportion, in order to be more confident, we're going to get a wider interval, okay? Because the only way we can add confidence is to perhaps broaden the scope. If we want to be 99% sure that the population proportion lies within the interval, it makes sense that that interval is going to span a wider range of values, because then we can be more confident. Whereas if we want less confidence, if we only want to be 90% confidence of it, then we're going to get a narrower interval, okay? Because we can be if we're less confident, then we can be more precise about our prediction, because it only has to contain the population proportion 90% of the time. That's one of the key ideas, this idea that the more confident you want to be, the wider your interval is going to need to be to capture that level of confidence, okay? The less confident you want to be, the more accurate your confidence interval will be able to be, but you'll be less confident in that narrower interval, okay? So it's a trade-off. So that's what it talks about down here. Note that in order to gain greater confidence, the interval will in fact capture the population proportion, a wider interval is required. Okay, we're going to talk about this margin of error, which comes up in the statistics that we get when we do the confidence interval on the CAS. So we know that a C% confidence interval is given by this, where this A value is related to the standard normal distribution. We can also write the confidence interval this way, which helps to illustrate that the confidence interval is symmetric about the sample estimate for the proportion. So P hat is the mean here, or is in the center of this distribution, and then we're adding on this value and we're taking away this value to get our 95% confidence interval. Or, well, if it was 95, then that would be 1.96, okay? So let me change that then, because in this instance that would be 1.96 because it's 95% confident. Okay, now the point is that this is essentially, we would call this the margin of error, okay? How far we're deviating away from that central value is our margin of error, okay? So the quantity that we're adding and subtracting each time, okay, that's the margin of error. So the margin of error is this A times the square root of P hat times 1 minus P hat over N, again, where that A value comes from that standard normal distribution. Alright, so a random survey of voters in a particular electorate is carried out. It's found that 25 of the 40 people surveyed prefer the Labor candidate. Find the margin of error for a 95% confidence interval. Okay, so the margin of error for a 95% confidence interval, it means it'll be 1.96 if it's 95%, and it's going to be the square root of, now, P hat here is 25 out of 40. So 25 out of 40 is 5/8 or 0.625. Okay, that right is 5/8, I think. N in this case was 40. Okay, so our margin of error, and it's going to be P, which is 5/8 times 1 minus P, which is 3/8 divided by N, which is 40. And it is approximate because we rounded that 1.96. Okay, so I'm going to go up and get my 1.96, which is right at the top now. There it is. So it's going to be that times the square root of, control divide, 5/8 times, times 3/8 over 40. And that is approximately, and again we haven't been given accuracy, makes sense to do 2 decimal places in this one, given the number. Margin of error is approximately 0.15. Okay. Now, if we'd used our rounded 1.96, let's just check whether that would have had a big impact. No, still 0.15. Obviously, we could also have used the CAS, so we could have used the menu 665. Our number of successes here is 25. Our N value is 40, 95% confidence level, and we would have got our margin of error calculated there as part of that as well. Okay. But for relatively simple numbers, this could come up tech-free, the margin of error a bit. It's not that bad a formula, and things like that. So just be careful about always relying on the CAS. Part B, another random survey of voters in the same electorate is carried out. It's found that 250 out of the 400 people surveyed preferred the Labor candidate. Find the margin of error. Okay, so in this case, N is 400. P hat is 250 out of 400, which is the same as 25 out of 40, so it's still 5/8. Okay, so the only thing that's changed is the 400. So our margin of error here, still a 95% confidence interval, so it's 1.96 times the square root of, this is still 5/8 over 3/8. So the only difference in the calculation is instead of dividing by 40, we're now dividing by 400. And so therefore we would expect that if we're dividing by a bigger number, we're going to be making the margin of error smaller. Okay, so let's just check that with this by hand calculation. In fact, I might just edit this previous one, because all I need to do is change the 40 to 400. And we find that is 0.047. So we've actually got quite a lot lower margin of error. It's nearly 3 times lower. By increasing the sample size. Okay, it's the everything else is the same. The proportions are the same. But if we have a larger sample size, our margin of error is going to be smaller. And the margin of error is about defining the width of your confidence interval. So hence the width of the confidence interval, okay, is going to be smaller. The larger the sample size, the more accurate your confidence interval will be able to be. And so that's the key too. Bigger the sample size, smaller the margin of error, hence narrower the confidence interval. Comment on the effect of the sample size on the margin of error. Larger sample size means smaller margin of error. Okay, so hence narrower confidence interval. Okay, that's a really important idea as well. Alright, example 4. A Labor Party candidate wishes to get a sense of the opinions of those in his electorate with regard to same-sex marriage. Previous surveys have indicated that about 70% of voters in this electorate are pro same-sex marriage. This is obviously an electorate where same-sex marriage is not currently legal. Determine the size of the sample required to get a margin of error of 3% in an approximate confidence interval of 0.95 for the proportion of voters in this electorate who are pro same-sex marriage. Okay, so we know that margin of error for a 95% confidence interval is 1.96 times the square root of p hat times 1 minus p hat over n. Okay, so we know the margin of error is 3%. The confidence interval of 95% is what's defined this number. And we've got p. Well, we can use that as an approximation for p hat. So we want to work out what does the sample size have to be to ensure a margin of error of 3%. So if the margin of error has to be 3%, which is 0.03, that to be 196 times the square root of, we're going to use the population proportion or the previous sample proportions as an estimate for this sample proportion, so 0.7 times 0.3 over n. We want to solve that for n. So menu 31, 0.03 equals 1.96 times the square root of, control divide, 0.7 times 0.3 over n. We want to solve for n. And we find that the sample size would need to be to the nearest person 896. Now sometimes you do need to be a bit careful of the rounding. So if we were to just quickly calculate 1.96 times the square root of 0.7 times 0.3 over 896. Yes, we do actually get a margin of error just over 0.3. So rounding down is okay. If the number had been such that we'd had to round up to 897, we would have found that our margin of error is actually just under just under 3% or 0.03. And so we do sometimes need to be careful about the rounding. So you're going to need to round down to ensure that you get at least that level of confidence. Okay. So n is, if the sample size is approximately 896, then we can ensure that we'll get a margin of error of only 3%. So if we want to work out, okay, what margin of error are we comfortable with, that determines then, well, how big a sample do we need to take. Determine the size of the sample required to get a margin of error of 2%. Okay, so if we actually wanted a smaller margin of error this time, so if we want only 2% margin of error, let's have a look. Let's do the same calculation up here, but change the 0.03 to 0.02. We're going to need a much bigger sample if we want that smaller margin of error, and that makes sense. Now again, let's have a look at the rounding here. So to the nearest whole number, I'd be tempted to write 2017, okay? But if we have a look at, let's do this calculation here for 2017, let's just check. Sorry, 2017. We actually don't quite get the 2%, technically speaking. Okay, so again, we should be rounding down to 2016 to ensure that we do actually get that 2% margin of error. So 2016, we need to round down to ensure the margin of error of at least 2%. Okay. So just be careful with that. Sometimes it's to do with the phrasing of the question. It might be okay to round up. Just be clear about, often it'll say they want a margin of error of at least such and such a percent, in which case you want to make sure that your value of n will actually give you the margin of error that you need. Okay, confidence intervals is the last part of statistical inference, and it is the last part of probability and statistics, and it is the last part of the mathematical methods course. Well done. Finishing off exercise 17D, and then it's on to exam preparation.